Hey, this is Richard Rogers, and welcome to my video on regression diagnostics. Today we're going to deal with a problem that emerges in OLS regression. Now, when you're done with your OLS regression analysis, you've found the equation of the line, and you have a number for the goodness of fit, you might be tempted to think that you're done. However, just because the computer generated a bunch of numbers doesn't necessarily mean that we have a good fitting line yet. And so this is what we're going to look at. We're going to try to diagnose our regression analysis to see if there are any problems. Our particular concern is the error term. We want the error to be homoscedastic. What that means is we want the size of the error to be about the same across all values of our independent variables. Sometimes a picture is better than words, and we'll look at these two plots here to get a sense of what we mean. So these are what we call residual plots. We'll show you in a bit how to produce these in SPSS. On the y-axis, we have the residual, or the size of the error that we have from our model. And then on the x-axis, we have the predicted value. We don't want to see any pattern. We don't want to see any points sticking out. And when we see that, that means our model gives us a homoscedastic error. When we look at the top scatter plot, we see some issues. So up there in the upper left-hand corner of the spot, it looks like there might be a string of points that are reaching out away from the main cluster of points. And we see a kind of thinning of points over on the right-hand side. We don't know yet if this is a big problem, but it's something that we see visually. Compare this to the plot at the bottom. The plot at the bottom has less of a pattern to it. Now we do see some points sticking out, so we still want to check to see what's going on there. But it's not as pronounced as it is with the plot at the beginning, up in the top of the screen. So let's take a look at these and see what is going on. The topics that we'll be looking at with these are the residual plots themselves. We'll also be looking at tests for homoscedasticity and heteroscedasticity. And we'll also be paying attention to influence and leverage statistics. So the first equation we're going to look at, that we're going to do just simple ones today. We're going to take the log of the violent crime rate as our dependent variable, and we're going to regress it on the poverty rate. I'm not going to spend a lot of time looking at this slide here, but if you're in one of my classes, this is by now a well-known example to you. There are two ways that we can get a residual plot. So there is, with the linear regression procedure, an option to create these plots. And here I have selected a plot. I am putting that Z-resid stands for standardized residual, Z like in Z-score. So I've taken the standardized residual and put it on my y-axis, and the standardized predicted value and put it on the x-axis. And that's actually how I created the plots that we saw earlier in this video. If I have a multiple regression, I might also want to click this box that says produce all partial plots. And then what I'll get is a graph of the standardized residuals graphed on each independent variable, because I may get different patterns in the plots from one independent variable to the next. The other way to do it is to save the values to a data set. So there is a save function with the linear regression procedure, and so I can click on that. And then what happens is it sticks these new values at the end of your data set. So if you were to go to the variable view, you would see them down at the bottom of the screen. Or if you were to look at the data view, these would be the columns on the far right of the screen. And from there, you can use the graphs features of SPSS to make your own graphs. So you might want a real easy way to do these scatter plots that I'm showing you today is to go into the legacy dialogues and then select the plot that you want to use. So either way will bring you to the same end. So here is the scatter plot for the log of the violent crime rate regressed on the poverty rate. This is the one that is fairly good. I don't see anything right away that causes me panic, except maybe a few points scattered out away from the main cluster. There is a fairly simple test that I can do that gives me an indication that there may be something going on in the residuals. Um, the equation I ran was over in the linear regression procedure. For this test, we have to go over to the general linear model procedure and specifically to the univariate command. So that's where I am. In the options, we can select down. There's a variety of tests on here for homogeneity and heteroscedasticity. If we go down to heteroscedasticity tests, the one that's the easiest to use is the Brush-Pagan test. So I've checked that here, and then it will come out as part of our analysis. So here are the results for that regression of the violent crime rate on the poverty rate. And you'll see on the far right, the significance of the Brush-Pagan test is 0.179, which is greater than 0.05. We interpret this test the same way that we do any test for homoscedasticity, like we did with the Levine's test. So the null hypothesis is that I have homoscedasticity, which is what I want in this case. And so because it's greater than 0.05, I would assume that I do have homoscedasticity in the residuals. I would accept that null hypothesis. And I can proceed forward as if there is really no problem with the analysis. Only time I would probably overrule this if I was looking at the residual plot and I saw something that was obviously a problem um, that this numeric test didn't pick up. But I didn't really see anything there. I know that the plots are not going to be perfect, and this is telling me that although my residual plot is not perfect, there's not a lot there to worry about. Now let's look at the other plot. The other plot that I showed you, the first plot back on the screen with the two plots, has a very different outcome. And it says that we have heteroscedasticity when I apply the Brush-Pagan test. So let's go back and take a look at that equation and say, what can we do with that equation to address this situation? That model was determined by taking the log of the violent crime rate and regressing it on the population, specifically on the log of the population, because population is often skewed. As again, if you're in my classes, you know that by now. So here is the plot that we had before. And again, our issue is that upper left-hand corner and also that thin line on the right. Now I can, if I save the residuals and the predicted values to my data set, I can go and start looking up values. So you notice those 2 points that hang out way out there are Alaska and Delaware. And right away, I know that those are states with small population sizes. So immediately I'm going, oh, maybe there's something about population that I'm not picking up by using the log of population. Maybe it's a more complex variable that I can see. Now, when I look at a residual plot, it might be fairly obvious what's going on. But this case is a little more complicated because the issue might be population. And I already have a transformation in my model to adjust for the effects of population. So I think I may want to drill down some more. This is where influence and leverage statistics come in. The idea here is that there are points that may be unduly influencing our line. So we don't want a line that represents where one point is on the plot. We want a line that represents the largest number of points, the main cluster of points. And so we're looking for these things that might be pulling the line one way or another, and we don't always see them. Now, sometimes we might. So when we look at this, some of the things that we see in the residual plot might be confirmed, but there may be other things that we don't see. I'm looking at three: Cook's D, DFFITS, and the center leverage statistic. And to get those, we have to go back to the linear regression procedure. And we don't actually get those statistics out. They are numbers that are calculated for every observation. So we have to save them to our data set, and then we have to create our own scatter plot in order to look at the patterns. Here's the first one, Cook's D. So on my dependent, on the y-axis, I put the log of violent crime rate, because this is about how the y variable affects the model. And then I put Cook's D on my x-axis, and I see 4 points standing out away from the main cluster of points. Because I have this data saved to my data set now, because that's the only way I could get it, I can actually go through and look them up. So what I did is I sorted that column for Cook's D in descending order, and I see 4 states, Alaska and Delaware, which we already encountered, and 2 additional ones, Vermont and Maine. Again, all low population states. Here's DFFITS. DFFITS also looks at the contribution of the dependent variable to the model. It's a different look. With DFFITS, there's a calculation here. We have to do this by hand, but it is the threshold that we have to cross in order to think that we have some sort of undue influence occurring within the model. And that, for this model, I have it there. It's the number of variables and number of observations that we use. And there the absolute value is 0.4. If I look at my DFFITS axis, none of the states that stick out, so it's the 4 states that we had from Cook's D, none of them actually stick out. All of them are within 0.4, are less than the absolute value of 0.4. So although Cook's D is signaling something might be happening there, DFFITS is saying maybe not. Maybe this is not a big issue. Yeah, the points are sticking out, but not so much that I actually care. Now, the centered leverage statistic looks at how the independent variable or variables are pulling the line. So on my x-axis, I put the independent variable. Now, the centered leverage statistic is looking at how the independent variable or variables are pulling the line. So I put the independent variable here on the x-axis, and I put the center leverage value on the y. And you'll see that curvilinear shape. But as with some of the other things, we don't care about most of these points. We only care, we have the equation up here, which is kind of the rule of thumb. We only care if we pass a certain threshold. And that threshold in this case is 0.08. And I graphed where I put 0.08. It's the red line here on the graph. And we see that 1 point stands outside of that, California. California is a candidate for pulling this line. It may have undue leverage on our line. Again, it's in line with our population theme. Now, in the others, we had the small states sticking out, but on this one, we have California sticking out. So again, it's the largest population state, so it has something to do with population. So we have different stats that are giving us different answers to the question, and the question is, which statistic is the best? And the answer is all of them. You've got to look at all of them. And this is the point where we have to start making judgments when we get all of this information in. And this may cause us to change our regression and do it over again, or we might end up keeping the regression that we have. Because there are so many possible situations, and each analysis is unique, there could even be compound issues, it's hard for me to tell you exactly what to do. Some of it's experience, but some of it's common sense. So what we need to do is list out some of the sources of heteroscedasticity and think about what they look like on plots. So with outliers and clusters of points, what we're going to see are those individual points that are going to stand out away from the main cluster of points. So we're going to see that right away. So we can then go back and save the residuals and the predicted values and look up exactly what those places are, and then figure out the correct strategy. Critical mass introduces the idea of a threshold effect, that certain things might not happen till a place reaches a certain size. For example, let's suppose I'm counting up how many newspapers a town has. Well, really small rural towns often don't have newspapers because there's not enough people to make that a profitable business. So that's going to create some unusual patterns in our residuals that we would have to deal with. Next, there's the idea of non-normality, and I have a specific example here. Um, this is an analysis that was done on some data uh, where population was one of the independent variables, and you'll notice that there's a curvilinear effect in the residual plot. So this tells me that I may want to transform a variable, uh, and to go back to square one in my analysis and transform that variable, and then I'd have to work through the whole analysis again. The other issue I want to raise is the issue of counts. So this is when I go through and I count events. Um, when I count events, uh, sometimes there's lots of places that have no or a few number of events, and some places that have a lot. That produces a known pattern in our residuals. And here it is. It's a fan-shaped plot. So this is where I'm counting up the number of violent crimes per county in the United States. And what you'll notice is that there's greater variation in the residual plot in the error term as I go up. Now, the outliers in the far right, those are just strange cases. But when I go the first 2/3, going up the independent axis, the first 2/3 of these values, of these points, you can see that as the predicted value increases, that the dispersion that we see in the error term also increases. So there are particular strategies. In this case, it suggests looking at a Poisson or negative binomial model. Um, if you see it, you should be smart enough to at least ask, how do I fix something like this? Because this is one of those things where you probably need some experience looking at it. But because in my classes we have a lot of criminal justice students, this is actually an issue that comes up and that they write about in the literature. How do we deal with this fan-shaped distribution? So what do we do if this happens and we discover a problem? Um, again, because there's so many possibilities, I can't give you one single answer. But I can tell you what some of the options are. You might decide to leave something unchanged. So you work through some of the obvious options and issues, and then when you run the new model, you discover you have almost the exactly same result as the old model. In that case, you might want to just go with the original model, and mention in your methodology section, maybe as part of your analytic strategy, that you tried this other model, but because it was essentially the same, you stayed with the original model. Uh, the looking at the residuals might find a place where you did not do a transformation that should have been done, or you might not have been aware that it needed to be done. It could also lead you to do the opposite. So I found situations when so many variables get transformed, because that's what you're supposed to do, with those variables back way in the early steps. You're supposed to see if you can make the variable normal. Sometimes making all of the variables normal actually makes the residuals indicate a curvilinear relationship that shouldn't be there. So you might have to actually go back and untransform something. You might change statistical procedures, and that's what I was mentioning with counts. You might conclude that OLS regression is not the correct procedure to use for your data. You could do what some people have done, and if it's just a few isolated points, just remove the outliers. Um, and just say it in your methodology section. These places were outliers. We don't like to remove points, but part of the thing is you do want your regression line to represent the greatest number of points. And if there are 2 or 3 points that are pulling the line or exerting undue influence, you don't want your model to be determined by a small number of points. Now, better than outliers, many people today are now adding a weight. So let's look at that. The idea behind a weight is that we will count part of the variable, but we will discount it if it's far away from the main cluster of points. So there are a variety of weights out there. The simplest one to calculate might be the Huber weight. The Huber weight, we're gonna start with a number that we're gonna call k, like k equals 1.345 times the standard deviation of our dependent variable. Now you're gonna before you say that, oh, 1.345, did this number fall out of the universe or something? We did something similar to this when we were trying to define an outlier. So there it was, 1.5 times the interquartile range to locate that point. So Huber's doing the similar kind of thing and putting us roughly at the same spot. Not exactly, because it's a different kind of calculation, but notionally it's about the same. So you have to be far away in order to have this discount applied. Now that's the start of the weight. So to determine the weight, if our error term is the absolute value of our error term, because our error term can be positive or negative, the absolute value of the error term is less than 1.345 times the standard deviation, or k. So if the error term is less than k, my weight is going to be 1. In other words, I'm not going to change anything. It's within an acceptable range. If my absolute value for my error term is greater than k, then I'm going to calculate this weight here. So k divided by my error term. Now, what happens? Well, if the error term, if k is just slightly smaller than the error term, I'm going to get a value close to 1. But if the error term was ridiculously huge, that's going to move closer and closer to 0. Now, the logic in statistics is, even if I have a small number um, for my weight, I'm gonna discount that point a great deal. Having it there is still more accurate than completely removing that point. So let's say the weight is, in my weight, it's 0.2. Counting 20% of that point is probably better than not counting that point at all. I do have to account for the fact that there's this wild value out there. I don't want that wild value to determine what my line is, but I need to account for it. And the Huber weight does that. Now, let me just throw out a caution, because it's pretty easy to abuse this. We shouldn't be using the Huber weight to correct for other problems. We should be using the Huber weight only when we have these very random things. So like in the analysis we just looked at, we may have an issue there with population. We can't transform our way out of that analysis because we've already done the transformation. So the Huber weight might be a way to fix that analysis. Now we won't know till we actually do it, but the Huber weight could be a solution to that. Where do I put it? What essentially happens is we're now creating what's called a weighted least squares regression. And you'll notice in the bottom of the linear regression box, there's something that says WLS weight. So if I went and calculated a Huber weight, and by the way, I would do that under compute variables. So if I calculated my Huber weight, I could put it in there. And I have a similar box in the univariate procedure. So either regression procedure, I can use the Huber weight. Okay, so what just happened? I sometimes say that statistics looks more like art than science, because you have to make some sort of judgments. They could be very idiosyncratic to you. And this is one of those places. The important thing is that you do look at your OLS regression. You do try to diagnose whether or not they're problems. Your solution might not be the same as someone else's, but if you actually do go through there and can say, I looked at issues X, Y, and Z, if someone were to ask questions about that at a conference, or there would be a discussion about something you published, you would be able to say, yes, I looked at it and this was my solution. And then the nature of that conversation changes. Um, on some topics, like with crime rates, you may find in the literature that there's already a discussion about what the correct approach is when you see a certain problem. But that doesn't exist everywhere. So don't assume that that's there. But if you do encounter that, you will know. You will then know if you go to a conference and you're presenting your work that your peers would be expecting you to look at that issue if something that triggers that issue appears. So that's it. I hope this was informative and good luck with this. This is a complicated topic, but it uh, certainly helps us make every analysis unique and different. Thanks. Bye.